Every time you gaze up at the night sky, you're not just looking at distant points of light, you're staring into a vast, shimmering storybook written across the cosmos. Each star is more than a burning ball of gas. It's a keeper of ancient secrets, a witness to events so grand they defy human imagination. Think about the last time you stood beneath a canopy of stars. That sense of wonder you felt, that's the universe whispering to you, inviting you to listen to tales older than time itself. From the fiery birth of galaxies to the silent collapse of dying suns, every flicker of light holds a chapter in the greatest story ever told, one that we're only beginning to understand. Long before telescopes or satellites, our ancestors looked up and saw more than just stars. They saw gods, heroes, and mythical beasts etched into the heavens. The Greeks traced Orion's belt, the Inuit saw celestial hunters, and the Maya mapped the movements of Venus as a divine messenger. These weren't just stories, they were humanity's first attempts to decode the cosmos. Today, we've traded myth for science, but the mystery remains. Modern astronomers peer into the hearts of stars and find elements forged in supernovae, the same atoms that make up your body, your breath, even the device you're holding right now. The stars didn't just tell stories, they created us, and now we're learning to read their language. What if I told you the night sky is hiding more than we ever dreamed? Beyond the constellations and familiar planets lie cosmic riddles that challenge everything we know. Some stars pulse with rhythms we can't explain, others vanish without a trace, and a few might even be signaling to us across the void. This video is your ticket to unraveling those enigmas. We'll travel from the birth cries of newborn stars to the ghostly echoes of black holes, uncovering how each celestial body carries a legacy that stretches across eons. By the time we're done, you'll never look at the stars the same way again because you'll realize they've been speaking to you all along. All you had to do was listen. Picture a vast, swirling cloud in space, dark, cold, and seemingly lifeless. But hidden within that cosmic dust lies the seed of a future star, a story waiting to unfold. Gravity begins pulling these scattered particles together, slowly at first, then with unstoppable force. As the cloud collapses, it spins faster, heating up until the core becomes a seething furnace. Then, in a flash of light, nuclear fusion ignites and a star is born. This isn't just physics, it's the universe's way of writing its next epic. The Orion Nebula, that glowing smudge in the winter sky, is one of these active nurseries. Inside its glowing folds, newborn stars blaze to life, casting off the remnants of their dusty cradles like cosmic infants taking their first breaths. But here's the haunting truth. The material that forms stars is the same stardust that once made up everything around us. The iron in your blood, the calcium in your bones, they were forged in the hearts of long-dead stars. So when you look at a newborn star, you're not just witnessing a distant event. You're seeing the recycling of the very elements that will one day build new worlds, new life, maybe even new storytellers. Cultures throughout history understood this instinctively. The Maori saw star birth as the separation of sky and earth. Hindu texts described stars as divine sparks. Even modern scientists speak of stellar nurseries with a reverence that borders on poetry. What's astonishing is how long this process takes. A star like our sun spends millions of years in gestation before its first flicker of light. Yet across the universe, this drama plays out constantly. In the Carina Nebula's towering pillars, in the Eagle Nebula's glowing tendrils, in countless unseen corners of space. Each new star carries a unique signature, a chemical fingerprint telling the story of its origins. Some will live quiet lives, burning steadily for billions of years. Others will blaze brightly and die young, scattering their enriched remains across the galaxy in spectacular supernova. But all of them, from the humblest red dwarf to the most massive blue giant, begin the same way, as whispers in the dark, gathering themselves into light. Ancient civilizations didn't just see random dots in the sky, they saw the canvas of their deepest beliefs. Take Orion, that bold hunter striding across the winter heavens. To the Greeks, he was a giant slain by Artemis, forever chasing the Pleiades. But halfway across the world, the Lakota people saw his belt as the spine of a bison, while Aboriginal Australians traced those same stars as a canoe carrying ancestral heroes. These weren't mere coincidences, they were proof that under the same night sky, humanity's imagination could spin countless tales from the same starlight. The Egyptians aligned their pyramids with Orion's belt, believing the pharaohs would join those stars in the afterlife. Meanwhile, the Maya tracked Venus with such precision they timed wars to its appearances, convinced the planet was a divine messenger. And in the Arctic, the Inuit saw the Milky Way not as a river, but as a snowy path for departed souls. What's astonishing isn't just the diversity of these stories, it's how they all served the same purpose, making sense of the terrifying vastness above. Without telescopes or equations, our ancestors used myths like celestial roadmaps, turning chaos into order with nothing but observation and wonder. Even now, these ancient interpretations linger in unexpected places. The word disaster comes from the Latin for bad star, a relic of astrology's influence, the 7-day week that traces back to Babylonian star worshippers who named days after the 7 visible wanderers: Sun, Moon, Mars, Mercury, Jupiter, Venus, and Saturn. And when you wish upon a shooting star, you're channeling a tradition older than Rome, where people believed falling stars carried the souls of the departed. Science may have replaced superstition, but the poetry of those early stargazers still tints how we see the cosmos today. Their stories remind us that astronomy didn't begin in observatories. It began around campfires, with upturned faces and questions whispered to the dark. Stars don't simply burn, they live. Their existence unfolds in chapters as gripping as any epic, each phase a dramatic transformation written in light and gravity. Take our own sun, that familiar golden disk in the sky. Right now, it's in the prime of its life, a main sequence star steadily fusing hydrogen into helium at its core. But this stability is just one act in a much grander story. 4.6 billion years from now, the sun will exhaust its hydrogen fuel, swelling into a red giant so vast it could swallow Mercury, Venus, and possibly Earth whole. Then, in a final act of cosmic poetry, it will shed its outer layers, leaving behind a dense, glowing ember, a white dwarf that will cool over trillions of years, fading into the dark like the last whisper of a forgotten tale. Yet this gentle demise is just one possible ending. For stars 8 times more massive than our sun, death arrives with fireworks. As their cores collapse under their own weight, temperatures soar to unimaginable heights, forging elements like gold, silver, and uranium in seconds. Then boom, a supernova tears the star apart, outshining entire galaxies for weeks. These explosions are more than just spectacular light shows. They're cosmic alchemists, scattering stardust across space that will one day form planets, oceans, even life itself. The Crab Nebula, that wispy remnant visible through amateur telescopes, was once a star whose violent death in the year 1054 was recorded by Chinese astronomers. Today, its swirling gases still race outward at 1,000 miles per second, carrying the legacy of that cataclysm across the centuries. What's haunting is how these life cycles mirror our own myths of creation and destruction. Hindu cosmology speaks of the universe breathing in and out, expanding and collapsing in cycles eerily similar to stellar evolution. Norse legends describe the world tree Yggdrasil, its roots and branches mirroring the structure of galaxies. Even the phoenix, reborn from its own ashes, finds a parallel in supernova seeding new stars from their debris. Science has given us the mechanics of these processes, but the awe they inspire remains unchanged. When you grasp that every carbon atom in your body was forged in a dying star's fiery heart, you realize we're not just observers of these cosmic stories, we're characters in them. The universe keeps no two stellar lives identical. Smaller red dwarfs, barely a tenth the sun's mass, burn so slowly they could outlast the current age of the universe by trillions of years. At the other extreme, hypergiants like UY Scuti are so colossal that if placed at our solar system's center, they'd extend past Jupiter's orbit but live fast and die young, lasting only a few million years. Then there are the mysterious neutron stars, remnants of supernova so dense that a sugar cube-sized chunk would weigh as much as a mountain. Some of these spin hundreds of times per second, becoming pulsars that flash like cosmic lighthouses. Others, locked in binary systems, slowly devour their companions in a dance that emits X-rays visible across the galaxy. Perhaps the most profound lesson lies in stellar deaths. When massive stars collapse, they sometimes leave behind black holes, gravity's ultimate victory, where not even light can escape. Yet even these cosmic voids play a role in the story. The supermassive black holes at galaxy centers shape their homes like invisible architects, while smaller ones might quietly wander the Milky Way, unseen but influential. It's a reminder that in the cosmos, endings are never truly final. A star's death plants the seeds for new solar systems, just as winter's frost prepares the Earth for spring. This cyclical nature ties us to the stars in ways we're only beginning to understand, not just through shared atoms, but through shared rhythms of renewal written into the fabric of space and time. There's a moment in every massive star's life when it realizes the show can't go on, when the nuclear furnace at its core runs dry and gravity takes the stage with brutal finality. In that instant, the star's outer layers collapse inward at a quarter the speed of light, then rebound in a shockwave so powerful it rips the star apart. This is a supernova, nature's most spectacular fireworks display, a blast so bright it can outshine an entire galaxy for weeks. But what makes these explosions truly extraordinary isn't just their violence, it's what they leave behind. In the heart of that chaos, temperatures soar past 100 billion degrees, forging elements like gold, platinum, and uranium in seconds. The next time you hold a wedding ring or glance at a digital clock, remember, those metals were born in a star's last, desperate moments, scattered across space like cosmic confetti. History is littered with accounts of these celestial dramas. In the year 1054, Chinese astronomers recorded a guest star in Taurus so bright it was visible for 23 days, even at noon. Today, we know it as the Crab Nebula, its tangled filaments still expanding at 1,000 miles per second. Half a world away, ancestral Publones may have painted that same supernova on canyon walls, while Aboriginal Australians possibly wove it into oral traditions about sky spirits. These weren't just observations, they were humanity's first attempts to document the universe rewriting itself. Fast forward to 1987, when a supernova erupted in the Large Magellanic Cloud close enough to see with the naked eye. Modern telescopes caught elements like nickel and cobalt spraying into space, giving us front-row seats to the alchemy that builds planets. Yet supernova aren't just relics of the past, they're shaping the future of cosmology. When scientists discovered the universe's expansion was accelerating, It was supernova that revealed the culprit, dark energy. By measuring how these explosions dim with distance, astronomers use them as cosmic yardsticks, mapping the invisible forces stretching spacetime itself. Some researchers even suspect supernova might have triggered the birth of our solar system, their shock waves compressing gas clouds until new stars ignited. It's a humbling thought that the very event that obliterates a star could also cradle the beginnings of life elsewhere. The aftermath of a supernova is where the real magic happens. In the wreckage, neutron stars spin like frenetic lighthouses. Their magnetic fields a trillion times stronger than Earth's. Some, called pulsars, beam radiation so precisely they rival atomic clocks. Others collide in kilonovae, creating gravitational waves and showers of gold. And if the dying star was especially massive, its core collapses into a black hole, warping space and time around it. But even here, the story doesn't end. The Cassiopeia, a supernova remnant, for instance, glows with tendrils of oxygen and sulfur, ingredients for future worlds. Meanwhile, the famous pillars of creation in the Eagle Nebula owe their sculpted forms to long-ago supernova shockwaves. What's breathtaking is how these explosions bridge myth and science. The Norse believed the world would end in fire with Ragnarök, a prophecy echoing the fate of stars. Modern astrophysics tells us supernovas seed galaxies with the stuff of life, from the calcium in your bones to the iodine in your thyroid. They're destroyers and creators, chaos and renewal wrapped in one luminous package. So when you look at the Veil Nebula's delicate filaments or the Vela remnant's ghostly glow, you're not just seeing a dead star. You're witnessing a cosmic relay race where one stellar generation passes its elements to the next, and in that handoff, writes the recipe for everything, including you. Imagine a city-sized object so dense that a single teaspoon of it would weigh 1 billion tons. This isn't science fiction, it's a neutron star, the collapsed core of a once mighty sun, crushed into existence by a supernova's fury. Left behind when massive stars explode, these remnants are nature's most extreme physics laboratories, where matter is squeezed so tightly that protons and electrons merge into neutrons, leaving behind a spinning, magnetized sphere with gravity 100 billion times stronger than Earth's. But the real magic happens when neutron stars beam radiation into space like interstellar lighthouses. We call these cosmic strobe lights pulsars, and their precision defies belief. Some spin hundreds of times per second, flashing with a regularity that rivals the most advanced atomic clocks on Earth. The Crab pulsar, born in the same explosion witnessed by Chinese astronomers in 1054, still whirls 30 times every second, its rhythmic pulses detectable across millennia. What's astonishing is how these cosmic timekeepers shape our understanding of the universe. In 1967, Jocelyn Bell Burnell detected the first pulsar signals, so unnaturally regular they were briefly nicknamed LGM for Little Green Men. Today, we know their pulses are the result of beams sweeping past Earth as the star rotates, like a spinning lighthouse casting light across a dark sea. Some pulsars, like PSR B1913+16, have helped confirm Einstein's theory of general relativity by the way their orbits decay, radiating gravitational waves. Others, like millisecond pulsars, spin faster than blender blades, accelerated by stealing material from companion stars. These ultra-precise cosmic metronomes are so reliable that astronomers have proposed using networks of them as galactic GPS systems, with pulsar timing arrays potentially guiding future spacecraft across the Milky Way. Yet neutron stars aren't just celestial curiosities, they're storytellers. Their surface magnetic fields can be a quadrillion times stronger than Earth's, twisting spacetime itself. When two neutron stars collide, as observed in 2017, they create kilonova explosions that forge gold, platinum, and other heavy elements in seconds. That event, detected by both gravitational waves and light, proved these collisions are cosmic gold factories, scattering precious metals across galaxies. Even more intriguing are the planets found orbiting pulsars like Pulsar B 1257+12. Bathed in lethal radiation, these worlds defy expectations. How could anything survive such hostility? Yet their existence hints at the tenacity of planetary formation, suggesting life might find footholds in the unlikeliest places. The poetry of neutron stars lies in their duality. Born from destruction, they become instruments of astonishing order. Take the Vela pulsar, its ghostly glow flickering 11 times a second while shooting a jet of particles at half-light speed. Or magnetars, neutron stars with magnetic fields so intense they could strip data from credit cards 100,000 miles away, occasionally unleashing starquakes that release gamma-ray flares visible across the universe. These objects stretch our imagination, proving that even in death, stars don't just fade away. They transform into something stranger and more magnificent. Every pulse, every flare, every gravitational ripple carries encrypted secrets about the laws of physics under conditions we could never recreate on Earth. Perhaps the most humbling thought is this: neutron stars are time capsules. They'll outlive every star now shining, spinning steadily as the universe cools over trillions of years. Long after galaxies dim, these dense remnants will keep their silent watch, flashing in the darkness like cosmic heartbeats, a reminder that even in the void, rhythm endures. When you grasp that their precise ticks are the calibrated footsteps of a dead star's legacy, you realize neutron stars aren't just objects in space. They're the universe's way of turning chaos into clockwork, destruction into dance, and their story, written in pulses and gravity, is far from over. Black holes aren't just cosmic vacuums, they're the universe's most enigmatic scribes, rewriting the rules of reality with every gravitational whisper. Picture the final moments of a star 20 times more massive than our Sun. After burning through its fuel, it collapses under its own weight, imploding with such force that even light can't escape its grip. What remains isn't just an object but a tear in the fabric of spacetime itself, a singularity where density becomes infinite and known physics simply stops. To stand at the edge of a black hole's event horizon would be to witness time itself slow to a crawl, as gravity stretches seconds into eternities. Yet for all their destructive reputation, black holes might also be creators. The supermassive ones at galaxy centers, like Sagittarius, a star in our Milky Way, act as gravitational anchors, shaping the orbits of stars and perhaps even enabling life by stabilizing their cosmic neighborhoods. The paradox of black holes lies in their duality. They're both tomb and cradle. When two black holes spiral toward collision, they ripple spacetime with gravitational waves, a phenomenon first detected in 2015 by LIGO. These ripples carry echoes of the merger, revealing details about the black hole's masses and spins like cosmic fingerprints. Meanwhile, the accretion disks of superheated gas swirling around active black holes blaze with light, outshining entire galaxies. Quasars, powered by these voracious giants, are visible across the universe, their beams piercing billions of light years as beacons from the early cosmos. Even Hawking radiation, the faint glow theorized to escape black holes, suggests they're not entirely black, just obscenely patient. A black hole the mass of our Sun would take 66 octillion years to evaporate, leaving behind only a whisper of energy as its final epitaph. What truly bends the mind are the theoretical possibilities lurking beyond a black hole's event horizon. Some models propose they could tunnel into white holes, hypothetical cosmic exits where matter spews back out. Others suggest they're portals to other universes, with Einstein's equations hinting at bridges called wormholes. While these ideas remain speculative, they've fueled countless stories, from Interstellar's Tesseract to the time-bending monolith in 2001, A Space Odyssey. Even the names we've given black holes reflect their mystique. Cygnus X1, the first confirmed black hole, sounds like a celestial supervillain, while Ton 618, a distant quasar, shines with the brightness of 60 trillion suns. Yet black holes aren't just theoretical oddities, they're essential players in the cosmic story. Without them, heavy elements forged in supernova might never have scattered across galaxies. Their mergers seed spacetime with gravitational waves, offering astronomers an entirely new way to hear the universe. And their sheer existence forces us to confront the limits of human knowledge, proving that some of nature's most profound truths are written in a language we're still learning to read. The next time you look at the dark patch near Sagittarius where our galaxy's central black hole lurks, remember, you're not just seeing emptiness, you're staring at a cosmic question mark, a riddle wrapped in a singularity, and the answer might just rewrite everything we think we know. Every star has the potential to be more than just a brilliant point of light. It could be the sun of an entirely alien world, casting its glow over landscapes we can only imagine. Take Kepler 186f, a planet 500 light-years away orbiting a dim red sun. It sits in the so-called Goldilocks Zone, where temperatures might allow liquid water to pool on its surface. Or consider the TRAPPIST-1 system, where 7 Earth-sized planets circle their stars so closely that a year there lasts mere days. These aren't just astronomical curiosities, they're testaments to the staggering variety of worlds the universe has crafted. Some might be barren rocks, others frozen wastelands, but a few could harbor conditions ripe for life, turning their parent stars into cosmic lighthouses signaling across the void. The hunt for these distant worlds reads like a detective story written across the cosmos. Astronomers don't actually see most exoplanets directly. Instead, they catch shadows as planets transit their stars or detect subtle stellar wobbles caused by gravitational tugs. It's like listening to a star's heartbeat and hearing the faint whisper of orbiting companions. The Kepler Space Telescope alone confirmed over 2,600 exoplanets this way, revealing that planets outnumber stars in our galaxy. Some of these systems defy imagination, like PSRB 1257+12, where planets orbit a dead pulsar, enduring its lethal radiation, or HD 189733b, a cobalt blue gas giant where it might rain molten glass sideways in 1,000-mile-per-hour winds. What makes these discoveries profound isn't just their strangeness, but what they imply about our place in the universe. When we find a world like Kepler 452b, dubbed Earth's cousin for its similar size and orbit, it forces us to wonder, if the universe builds so many Earth-like planets, how many might cradle life? The James Webb Space Telescope now peers at exoplanet atmospheres, searching for chemical signatures like oxygen or methane that could hint at biological activity. Imagine the moment when, not if we detect such signs around a star like Tau Ceti or Epsilon Eridani, both visible to the naked eye, suddenly every sunset on that world would carry the weight of an entire alien biosphere, its parent star transformed from a celestial object into a storyteller. Yet the true magic lies in the cosmic perspective these worlds offer. Around young stars like Beta Pictoris, we've witnessed planets forming in vast dusty disks, literal snapshots of solar systems under construction. Around white dwarfs, the corpses of sun-like stars, we've found shattered planetary remnants, glimpses of our solar system's eventual fate. and around dim red dwarfs, which outnumber all other stars combined, we've discovered rocky worlds like Proxima Centauri b, just 4 light-years away. These discoveries rewrite the narrative of planet formation, proving that worlds can thrive in environments once thought too harsh for complexity. Perhaps the most humbling thought is this: every star you see at night could be the center of its own epic. Some might host civilizations gazing back at our sun, wondering if it too nurtures life. Others might oversee frozen oceans or sulfur storms, their stories utterly alien yet no less magnificent. The next time you look up, remember, you're not just seeing stars, you're seeing potential homes, each with its own saga written in geology, chemistry, and maybe even biology. And as our telescopes grow sharper, we're not just mapping planets, we're learning to read the universe's richest anthology, one star and one world at a time. The Goldilocks Zone isn't just a region, it's a cosmic balancing act where a star's heat and a planet's chemistry perform an intricate dance. Too close to the sun and oceans boil away, too far and they freeze solid. But in that narrow, shimmering band of possibility, water can linger as a liquid, turning a barren rock into a canvas for life's story. Earth didn't just luck into this sweet spot. Our planet's size, atmosphere, and even its magnetic field all conspire to keep the delicate equilibrium. Yet what's breathtaking is how common these zones might be. Around cool, long-lived red dwarfs like Proxima Centauri, the habitable zone snuggles so close that planets complete orbits in days, tidally locking one face to eternal daylight and the other to endless night. Imagine a world where rivers might flow along the twilight line, or where life huddles in the narrow band between scorch and frost. But stars don't stay still, they evolve, and their Goldilocks zones migrate like shifting sand. A young, fiery star might push its habitable zone outward over billions of years, forcing life to adapt or perish. Giant stars, though short-lived, could briefly nurture planets before swelling into red giants and swallowing them whole. Even our sun's zone will creep outward as it ages, possibly rendering Mars habitable long after Earth becomes a desert. This cosmic game of musical chairs means that life, if it exists, might not just be about location, it's about timing. Some worlds could host fleeting oases in their star's youth, while others might awaken to life only in their star's twilight years. The real intrigue lies in the chemistry these zones enable. Water does more than quench thirst. It dissolves minerals, shapes landscapes, and acts as nature's universal solvent for biological reactions. On icy moons like Europa or Enceladus, tidal forces from their host planets might melt subsurface oceans, creating Goldilocks conditions far outside the traditional zone. Even Venus, now a hellscape, may have once been a temperate world before runaway greenhouse effects turned it into a warning. These exceptions prove that habitability isn't just about distance from a star, it's about a world's ability to trap, recycle, and protect its precious liquids. Astronomers now hunt these zones with tools that border on magic. The James Webb Space Telescope analyzes starlight filtered through exoplanet atmospheres, searching for water vapor, oxygen, or methane hints of a living world. Future missions like the Habitable Worlds Observatory aim to directly image Earth-like planets, capturing their pale blue dots in other solar systems. Each discovery rewrites the narrative. When we found LHS 1140b, a super-Earth in its star's habitable zone, or TOI 700d, a rocky world orbiting a quiet red dwarf, we didn't just catalog planets, we expanded the universe's potential for storytelling. What's profound is how this search mirrors humanity's oldest myths. The Babylonians tracked Venus as a goddess. The Maori saw constellations as navigational guides. Now we parse data for biosignatures, but the question remains the same. Are we alone? A single microbe found on an exoplanet would transform every star in the sky from a lantern into a question mark. Because if life can spark twice in one galaxy, then the universe isn't just vast, it's fertile, buzzing with narratives we've yet to hear. The Goldilocks Zone, then, isn't just a place. It's an invitation to listen closely, to wonder wildly, and to recognize that the stars above might not just harbor light, but life's untold chapters. Look up on a clear night, and many of those solitary-looking stars are actually pairs locked in an eternal waltz, binary systems where two stars orbit a shared center of gravity. These celestial duos don't just coexist, they interact in ways that rewrite the rules of stellar life cycles. Take Albireo in the constellation Cygnus. Through a small telescope, it resolves into a stunning gold and blue pair, one star blazing hot while the other glows cool, a cosmic yin and yang. But this visual harmony hides a deeper truth. Binary stars aren't just pretty pairings, they're laboratories for some of the universe's most dramatic physics. When binary stars orbit close enough, their gravitational tango can turn into a celestial heist. The more massive star ages faster, swelling into a red giant that spills its outer layers onto its companion, a process called mass transfer. In systems like Beta Lyrae, this stolen gas forms a glowing bridge between the stars, like two dancers sharing a veil. Sometimes, the donor star strips down to its dense core, becoming a white dwarf, while its partner gorges on extra fuel, burning brighter and longer than it ever could alone. It's a stellar second act written in stolen stardust. Then there are the eclipsing binaries, nature's perfect cosmic clocks. As these stars pass in front of each other from our vantage point, their combined light dims and brightens with metronomic precision. The Algol system, nicknamed the Demon Star by ancient astronomers, winks at us every 2.87 days like clockwork. These predictable eclipses let scientists measure stellar sizes, masses, and temperatures with extraordinary accuracy, as if the stars themselves are whispering their secrets through shadows. But binaries aren't always harmonious. In tight orbits, gravitational tides can distort stars into egg shapes, while intense radiation strips away atmospheres. Some, like Astrophotography, are recurrent nova systems where a white dwarf steadily siphons hydrogen from its companion until the stolen gas detonates in a thermonuclear blast, a stellar eruption repeating every few decades. And in the most extreme cases, binary stars meet a violent end. When two white dwarfs spiral inward, their collision can trigger a Type Ia supernova, an explosion so uniform astronomers use it to measure cosmic distances. These standard candles revealed the universe's accelerating expansion, proving binaries don't just tell their own stories, they help decode the cosmos itself. What's mesmerizing is how these partnerships challenge our ideas of solitude. Over half the stars in the Milky Way have companions, meaning single stars like our Sun might be the outliers. Some binaries even host planets in Figure 8 orbits around both stars, like Tatooine from Star Wars but real. Others, like Sirius, pair a brilliant main sequence star with a faint white dwarf, showing how stellar relationships evolve over eons. Whether they're gently transferring mass or locked in a death spiral, binary stars prove that even in the vast emptiness of space, no star is truly alone, and every cosmic dance leaves its mark on the universe's grand narrative. Some stars refuse to follow the script. They flicker, flare, and fade like cosmic actors improvising their lines. These are the variable stars, celestial mavericks whose brightness changes over time, sometimes predictably, sometimes with the drama of a plot twist. Take Delta Cephei, the prototype of Cepheid variables. It pulses rhythmically like a lighthouse in the void, growing brighter and dimmer over a 5.4-day cycle. What makes these stars extraordinary isn't just their rhythm. it's how they became the universe's yardsticks. Early last century, Henrietta Leavitt discovered a direct link between a Cepheid's pulse rate and its true brightness. Suddenly, astronomers had a tool to measure distances across the cosmos. By comparing how bright these stars appeared versus how bright they actually were, they could calculate how far away they and their host galaxies truly were. This breakthrough let Edwin Hubble prove the Andromeda Nebula was another galaxy, not just a cloud within our Milky Way. Every time you see a Cepheids flicker, you're watching a cosmic signpost, one that helped us map the expanding universe itself. Then there are the Mira variables, red giants with the slow, dramatic heartbeat of a cosmic elder. Named after Mira, the wonderful, in the constellation Cetus, these stars can take nearly a year to complete one pulsation cycle. As they expand and contract, their brightness may vary by a factor of 1,000, vanishing from naked eye view only to resurge months later. What drives this stellar breathing? Deep inside these aging stars, layers of helium and hydrogen alternately ionize and recombine, trapping heat and pushing the star's outer layers outward until they cool and collapse again. It's a feedback loop written in thermodynamics, creating luminosity changes visible across interstellar space. Mira itself, the original variable, was recorded by Chinese astronomers in the 14th century as a guest star, its reappearances noted like celestial clockwork. Today, we know these stars are shedding their outer layers, preparing to become planetary nebulae, proof that even in their twilight years, stars refuse to go quietly. But not all variable stars follow such orderly scripts. Cataclysmic variables live up to their name, erupting without warning in stellar tantrums that rewrite their systems. Picture a binary pair where a white dwarf siphons gas from its companion star. The stolen hydrogen piles up on the dwarf's surface until, boom, it detonates in a nova outburst, temporarily outshining the combined light of both stars. Some, like Astrophotography, repeat this cycle every few decades, while others build up pressure for centuries before unleashing their fury. Even more extreme are supernova, the ultimate stellar plot twists where entire stars self-destruct in explosions visible across galaxies. Yet these violent events serve a purpose, scattering heavy elements forged in their cores, seeding future generations of stars and planets. The beauty of variable stars lies in their duality. They're both cosmic clocks and chaos incarnate. Our Lyrae variables pulse with the regularity of metronomes, helping astronomers measure distances within our galaxy. Meanwhile, eruptive young stars like T Tauri blaze unpredictably as they settle into maturity, their magnetic tantrums flinging plasma into space. Some variables change brightness because they're eclipsed by companions. Others, like Betelgeuse, dim when massive convection cells bubble up to their surfaces like stellar lava lamps. Even our Sun has its subtle variability, its energy output shifting slightly over an 11-year cycle, a reminder that no star is perfectly steady. What's profound is how these stellar mood swings mirror human storytelling. Ancient cultures interpreted variable stars as omens or divine messages. The inconstant light of Algol symbolized the blinking eye of Medusa in Greek myth. Today, we see them as natural laboratories, their fluctuations revealing secrets about stellar interiors, evolution, and even the fate of our own sun. Whether they pulse like clockwork or erupt without warning, variable stars remind us that the universe loves a good plot twist and that even the most predictable seeming lights can harbor surprises. Their changes aren't flaws, they're features, each fluctuation a sentence in a story still being written across the night sky. When a star like our Sun exhales its final breath, it doesn't vanish, it leaves behind a ghost. White dwarfs are the universe's way of preserving stellar memories, packing the mass of a star into a sphere no larger than Earth. Picture a teaspoon of this material. It would weigh as much as an elephant, crushed into a crystalline lattice so dense that atoms lose their familiar shapes, becoming a quantum soup of electrons and nuclei. These cosmic tombstones glow with leftover heat, not fire. Their light comes from stored thermal energy, slowly radiating away over trillions of years like a fading ember in a cosmic hearth. Sirius B, the faint companion to the brightest star in our sky, was the first white dwarf discovered, its existence proving that stars could collapse into such bizarre states. What's haunting is how these stellar remnants evolve. A newborn white dwarf starts scorching hot, with surface temperatures exceeding 100,000 degrees hot enough to vaporize diamonds. But time cools even the fiercest flames. Over billions of years, the dwarf's glow shifts from blue-white to yellow, then red, and finally to infrared as it becomes a black dwarf, a cold, dark cinder adrift in space. The universe isn't old enough for any black dwarfs to exist yet, but their eventual fate is written in the laws of thermodynamics. Some white dwarfs don't fade quietly, though. Those in binary systems can siphon gas from companions, forming accretion disks that spark nova eruptions when accumulated hydrogen ignites. And if a white dwarf steals enough mass to cross the Chandrasekhar limit, about 1.4 times the Sun's mass, it detonates in a Type Ia supernova, obliterating itself in a blaze that briefly outshines galaxies. The most poetic white dwarfs may crystallize into cosmic diamonds. As they cool below 10,000 degrees, their carbon cores solidify into crystalline structures, essentially forming planet-sized gemstones. BPM 37093, nicknamed Lucy after the Beatles' song, is thought to be one such crystallized dwarf, its core hardened into a lattice of diamond. Imagine a celestial body where the core isn't molten rock, but a glittering matrix of carbon, a tombstone-turned treasure. Yet white dwarfs are more than just stellar relics, they're time capsules. Their atmospheres hold the purified remains of their progenitor stars, offering forensic clues about stellar chemistry. Some are polluted with heavier elements like calcium or iron, evidence they once shredded and consumed orbiting planets. Others, like GD362, have debris disks suggesting entire planetary systems survived the star's death throes. These details let astronomers reconstruct the final chapters of solar systems, revealing how stars like ours might one day leave behind wreckage for future civilizations to decipher. The quiet glow of a white dwarf is the universe's whisper of impermanence. Long after its parent star's fiery demise, it lingers as a memorial to cosmic cycles, proof that endings aren't truly final, just transformed. When you look toward the faint companions of bright stars like Sirius or Procyon, you're glimpsing the future of our own sun. Not a grand explosion, but a slow, dignified fade into the cosmic archive. And in that fading light, there's an odd comfort knowing that even stars, in their death, become keepers of stories far older than themselves. Here's the invisible scaffolding of the cosmos' dark matter, an unseen hand sculpting the universe's grand architecture. Though it emits no light, its gravitational pull weaves galaxies together like cosmic thread binding shimmering beads. Picture a spiderweb. You see the dewdrops glittering at dawn, but it's the invisible silk that gives them structure. That's dark matter's role, an unseen force keeping stars from flinging into the void. Without its hidden embrace, spiral galaxies like Andromeda would spin apart, their stars scattered like sand in a storm. Even stranger, this mysterious substance outweighs visible matter 5 to 1, meaning everything we see, every star, planet, and nebula, is just the glitter atop a vast, dark iceberg. Then there's dark energy, the universe's enigmatic accelerator. Imagine blowing up a balloon with invisible ink. As it expands, unseen forces stretch it faster and faster. That's the effect dark energy has on space-time itself. Discovered in the late 1990s when astronomers observed distant supernova dimming unexpectedly, this repulsive force counters gravity's pull, pushing galaxies apart at ever-increasing speeds. It's as if the cosmos has a hidden engine, one that's currently winning a tug of war against collapse. The numbers defy intuition. Dark energy accounts for roughly 68% of the universe's total energy, while dark matter makes up 27%. Together, they relegate the ordinary matter we know the stuff of planets and people to a mere 5% of existence. The hunt to decode these invisible narrators reads like a cosmic detective story. Scientists track dark matter's ghostly fingerprints through gravitational lensing, the way its mass bends light from distant galaxies like a funhouse mirror. Underground labs like Snollub shield detectors from cosmic rays, hoping to catch a rare collision with a hypothetical dark matter particle. Meanwhile, telescopes like Euclid and the Vera C. Rubin Observatory map the universe's expansion in 3D, tracing dark energy's influence across billions of years. Some theories suggest dark matter could be primordial black holes or exotic particles like WIMP. Others propose dark energy arises from quantum fluctuations in the vacuum of space itself. What's humbling is how these mysteries reframe our place in the cosmos. The stars we've mythologized, the galaxies we've mapped, they're just the visible ink on a page written largely in invisible ink. Ancient cultures worshipped sun gods. Modern physics tells us the true architects of the universe might be forces we can't even see. Yet every clue we uncover, from the bullet clusters separated dark and visible matter to the cosmic microwave background's subtle fluctuations, adds another sentence to this unfolding story. One day, solving these riddles might reveal why the universe looks the way it does, or even predict its ultimate fate. Until then, we're left with a profound truth: the grandest tales aren't always told in light. Sometimes the most epic narratives are whispered in the dark. The Milky Way isn't just a smear of light across the night sky. It's a sprawling library where every star is a book, every nebula a chapter, and every cluster a volume in the greatest story never fully told. With over 100 billion stars, our galaxy is a living archive, its oldest residents dating back nearly 13 billion years. These ancient stars, huddled in globular clusters like M13, carry the chemical fingerprints of the early universe, their atmospheres untouched by the heavy elements later generations would forge. Meanwhile, in the vibrant spiral arms, newborn stars blaze to life, their intense radiation sculpting glowing nebulae like the Orion Complex, where stellar winds carve cavities in the gas like cosmic fingerprints. At the heart of it all lies Sagittarius, a star, the Milky Way's supermassive black hole. This invisible leviathan, 4 million times heavier than our sun, orchestrates the dance of stars around it with silent gravitational authority. Nearby stars whip around it at thousands of miles per second, their frenzied orbits tracing the black hole's influence like iron filings revealing a magnet shape. Yet even this monster isn't alone. It's surrounded by a stellar graveyard, the remnants of stars torn apart by its tides, their material spiraling inward in glowing arcs visible only to X-ray telescopes. But the Milky Way's true magic lies in its diversity. In the galactic suburbs, solitary yellow dwarfs like our sun hum along quietly, their planets tucked into temperate orbits. Out in the halo, rogue stars speed through the darkness, ejected from their birthplaces by gravitational encounters. And weaving through it all are the galaxy's hidden narrators, pulsars that flash like lighthouses, magnetars with magnetic fields strong enough to warp atoms, and brown dwarfs, failed stars too cool to ignite fusion, glowing faintly like dying embers. What's astonishing is how much of this galactic story remains unread. Dark matter's invisible web holds the Milky Way together, its presence betrayed only by stars moving faster than visible matter can explain. Streams of stars torn from dwarf galaxies like the Sagittarius dwarf spiral through our own, their trajectories mapping ancient collisions. Even our solar system moves through space, orbiting the galactic center every 230 million years, meaning dinosaurs witnessed the Milky Way from a completely different vantage point than we do today. The Milky Way doesn't just host stars, it remembers them. Supernova remnants like the Veil Nebula lace the galaxy with threads of heavy elements, while planetary nebulae like the Ring Nebula showcase sun-like stars exhaling their final breaths into colorful shells. Every element heavier than helium in your body was forged in such stellar furnaces, meaning the galaxy isn't just around us, it's within us. From the myths that painted its haze as a river of souls to the modern probes mapping its spiral structure, the Milky Way has always been more than a sight. It's a mirror reflecting back our place in a story still being written, one starlit page at a time. The Andromeda Galaxy isn't just a faint smudge in the autumn sky, it's a mirror universe, a spiral island of over 1 trillion stars racing toward us at 250,000 miles per hour. In roughly 4 billion years, it will collide with the Milky Way in a slow-motion merger that will rewrite our night sky. Imagine looking up to see Andromeda's spiral arms stretching across the heavens, its dust lanes and star clusters blending with ours in a celestial waltz. Yet this cosmic crash won't be the violent explosion you might expect. Galaxies are mostly empty space, so stars will slide past each other like ghostly ships in the night, their paths bent by gravity but rarely crossing. Over billions of years, the two galaxies will entwine, their stars and gas swirling into a new hybrid galaxy astronomers call Milkdromeda, a glowing testament to the universe's endless reinvention. What's astonishing is how much Andromeda reveals about galactic life cycles. Its outer halo holds streams of stars ripped from smaller galaxies it's already consumed, like cosmic crumbs marking its past meals. At its heart, a supermassive black hole with 100 million times our Sun's mass lurks silently, surrounded by a dense cluster of ancient stars. Andromeda's disk sparkles with young blue stars, while its yellow core glows with older suns, telling a story of star formation that started long before our own galaxy took shape. Yet for all its majesty, Andromeda is just one of 2 trillion galaxies in the observable universe, each with its own unique biography waiting to be read. Take the Whirlpool Galaxy, a cosmic pinwheel 50 million light-years away where newborn stars ignite along spiral arms like strings of pearls. Its graceful curves are sculpted by a smaller companion galaxy tugging at its edges, triggering stellar nurseries in its wake. Then there's the Sombrero Galaxy, its brilliant bulge encircled by a dark dust lane that gives it the appearance of a celestial hat. This unusual shape hints at a turbulent past, possibly the aftermath of a galactic collision that left it both elegant and enigmatic. And in the depths of space, galaxies like Messier 82 blaze as starburst powerhouses, churning out stars 10 times faster than the Milky Way, their cores raging with the energy of supernova explosions. But not all galaxies are bustling metropolises. Some, like the sleepy elliptical galaxies found in dense clusters, are retirement communities for aging stars, their gas long since used up or stripped away. Others, like the ultra-diffuse Dragonfly 44, float like ghosts spanning as wide as the Milky Way but with hardly any stars, their mass hidden in dark matter. And then there's the mysterious Hoag's object, a perfect ring of blue stars surrounding a golden core, defying explanations of how such symmetry could form naturally. These galactic oddballs prove that the universe writes its stories in countless dialects, each one a variation on the theme of gravity, gas, and time. Peering even deeper, telescopes like Hubble and James Webb have captured galaxies from the universe's infancy, tiny, misshapen blobs of light emitted when the cosmos was just a few 100 million years old. These primordial galaxies, like GNZ11, glow with the light of stars forged from almost pure hydrogen, their simplicity a stark contrast to the complex spirals and ellipticals of today. Yet somehow, over billions of years, these humble beginnings gave rise to the galactic diversity we see now. The light reaching us from these distant island universes carries echoes of their past, allowing us to piece together their histories like detectives reconstructing a crime scene from scattered clues. Perhaps the most humbling realization is that every galaxy, from the nearest dwarf to the farthest quasar, is a collection of stellar stories interwoven with dark matter and gas. Their shapes, spirals, ellipticals, irregulars, are just the cover art for sagas written in gravitational interactions, collisions, and bursts of star formation. When you gaze at Andromeda through binoculars or see a Hubble image of the Cartwheel Galaxy's rippling rings, you're not just looking at objects in space. You're witnessing chapters in a story without end, where every twist reveals new questions about how the universe builds its grandest structures, and where we fit into that unimaginably vast narrative. Quasars aren't just bright, they're cosmic blowtorches, blazing with the energy of 1 trillion suns packed into a space no larger than our solar system. At their core lies a supermassive black hole, but unlike the quiet giants at galaxy centers, these are gluttons, devouring gas and stars at staggering rates. As matter spirals inward, friction heats it to millions of degrees, creating an accretion disk so luminous it can outshine every star in its host galaxy combined. The brightest quasars emit enough light in a single second to power human civilization for centuries, a ferocious beacon visible clear across the universe. What makes quasars extraordinary isn't just their brilliance, but their role as time machines. The light from the most distant quasars has traveled over 13 billion years to reach us, offering snapshots of the universe when it was less than 1 billion years old. Back then, galaxies were smaller, gas was abundant, and black holes feasted wildly, growing to monstrous sizes in cosmic infancy. Quasar J0319-1916, for example, anchors a black hole 2 billion times the Sun's mass, a behemoth that somehow formed when the universe was just a toddler. These objects shouldn't exist under current theories, yet there they are, forcing astronomers to rewrite the rules of how black holes grow. The violence of a quasar's feeding frenzy is matched only by its precision. Some blast jets of plasma at nearly light speed, stretching hundreds of thousands of light years into space. These jets, like the ones from Quasar 3C273, act as particle accelerators on a galactic scale, carving bubbles in intergalactic gas and seeding galaxy clusters with energy. Others flicker unpredictably, their brightness changing in days, a sign that the accretion disk feeding them is warped or clumpy, like water swirling down a chaotic drain. The quasar H0307+169 even shows signs of a relativistic hurricane, with winds so powerful they could sculpt entire galaxies. Yet quasars aren't just destroyers, they're cosmic architects. Their radiation can strip gas from surrounding galaxies, halting star formation in a process called quenching. Without these eruptions, galaxies like our Milky Way might have burned through their fuel too quickly, leaving no time for planets or life to form. Some quasars may even trigger star birth in distant gas clouds, their shockwaves compressing material until it collapses into new suns. It's a paradox. The same forces that obliterate matter also create the conditions for complexity. Today, most quasars are extinct, their black holes sated and silent. But their legacy lingers in the heavy elements they forged and the galaxies they shaped. When you look at a quasar spectrum, you're reading a chemical fingerprint: carbon, oxygen, iron, elements that will one day form planets and life. The light that took billions of years to reach us carries echoes of an era when the universe was raw, violent, and unimaginably creative. Quasars remind us that brilliance often comes from chaos, and that even the darkest hearts in space can light up the cosmos. The Big Bang often gets credited as the universe's opening act, but the real prologue was something far stranger. In the first trillionth of a trillionth of a trillionth of a second, space itself underwent a growth spurt so violent it defies analogy. Cosmic inflation wasn't just expansion. It was space-time stretching faster than light could chase it, doubling in size at least 60 times in a blink smaller than a quantum flicker. Picture a single atom swelling to the size of a galaxy cluster in less time than it takes light to cross that atom. This wasn't the gentle unfurling we see today. It was the universe rewriting the rules of physics to set the stage for everything that followed. What's astonishing is how this fleeting moment imprinted itself on the cosmos. Quantum fluctuations, tiny ripples in the fabric of reality, were stretched to cosmic scales during inflation, becoming the seeds for all structure we see today. Those microscopic wrinkles became the gravitational wells where matter pooled, eventually growing into galaxy clusters and the vast cosmic web. Without those primordial imperfections, the universe would be a featureless sea of particles, devoid of stars, planets, or life. The same process that smoothed the universe on large scales also left behind the tiny density variations that let galaxies take root. It's like blowing up a balloon with microscopic dust on its surface. As the balloon inflates, the specks separate, mapping the initial irregularities onto a grand canvas. The smoking gun for inflation hides in the oldest light we can see, the cosmic microwave background. This afterglow of the Big Bang, discovered accidentally in 1965, shows temperature variations of just 1 part in 100,000. The faint fingerprints of those quantum fluctuations magnified by inflation. Satellite maps from COBE, WMAP, and Planck reveal a pattern eerily consistent with inflationary predictions, a snapshot of the universe at 380,000 years old. The alignment is so precise it's like finding a fossil with its DNA perfectly preserved, confirming a theory about events that occurred 100 orders of magnitude smaller than an atom. Yet inflation isn't just about the past, it reshapes our future. Many models suggest our observable universe might be one bubble in a frothy multiverse, where other bubbles underwent different inflationary phases with their own physics. Some could harbor forces and particles unrecognizable to us, their very laws of nature rewritten in those first instants. This idea turns the cosmos into something akin to a cosmic quilt, with each patch stitched together by its own inflationary history. While still speculative, it hints that our universe's beginning might not be unique, just one variation in an infinite tapestry of possibilities. The poetry of inflation lies in its economy. A process lasting perhaps 10 to the minus 32 seconds determined the fate of a cosmos that would endure for billions of years. It turned quantum randomness into cosmic destiny, ensuring that when stars finally ignited, their light would have something to shine upon. The next time you gaze at the night sky, remember the vast spaces between galaxies, the delicate balance of matter and energy, even the fact that you exist to ponder it, all were written into existence in that first unimaginable moment. Inflation wasn't just the universe's opening chapter, it was the pen that wrote every story the cosmos would ever tell. What if our universe is just one page in an infinite cosmic library, where every book contains a completely different set of physical laws? The multiverse theory suggests exactly that, a reality where countless universes exist alongside ours, each with its own unique narrative written in the language of alternate physics. Some might have stars that burn with strange fuels, planets where gravity pushes instead of pulls, or dimensions where time flows backward like a rewinding film. In one universe, carbon-based life might thrive under a blue sun. In another, crystalline structures could think and dream in gravitational waves. The possibilities aren't just endless, they're beyond anything our singular universe could ever contain. Take the concept of bubble universes, where each cosmos floats like a soap bubble in an unimaginably vast foam. According to eternal inflation theory, space-time expands so rapidly that pockets pinch off into isolated universes, each with randomly determined constants. One bubble might have a stronger nuclear force, making stars burn out in millennia instead of billions of years. Another might lack electromagnetism altogether, leaving its skies perpetually dark. The eerie beauty of this idea: we'll never see these other bubbles, their light can't reach us across the inflationary divide. They're cosmic ghost stories, forever hidden yet theoretically lurking just beyond the edges of our reality. Then there's the brain-world hypothesis, where our universe is a three-dimensional membrane floating in higher dimensional space. Picture a loaf of bread where each slice is a separate universe, occasionally brushing against others. If true, stars in a neighboring brain might cast shadows we could detect as unexplained gravitational ripples. Some theories even suggest the Big Bang wasn't a singular birth but a collision between brains, a cosmic car crash that ignited our entire reality. The implications are staggering. What we call the universe might just be the aftermath of an interdimensional fender bender, with other wrecked universes drifting unseen in the higher dimensional void. Quantum mechanics adds another layer of strangeness with the many worlds interpretation. Every time a particle faces a choice, like whether to spin left or right, the universe splits, creating parallel timelines. In one branch, a star goes supernova. In another, it fizzles quietly. Over eons, these branching paths could spawn universes where Earth never formed, where dinosaurs still rule, or where you made a different choice this morning. Unlike bubble universes, these alternate realities share our initial conditions but diverge through quantum decisions, meaning somewhere out there, every possible version of cosmic history is playing out simultaneously. The multiverse doesn't just expand space, it explodes the very idea of storytelling. If every possible universe exists, then somewhere, a version of Orion hunts across a sky threaded with pink nebulas. Somewhere else, black holes sing in harmonies that shape entire civilizations. Ancient myths spoke of many worlds. Norse cosmology had Yggdrasil's 9 realms. Hindu texts described countless lokas, but modern physics gives these legends eerie new weight. The catch: we may never prove these alternate realities exist. They could be the ultimate cosmic inside joke, a theory that explains why our universe's laws seem so finely tuned for life. If every possibility exists, of course we'd find ourselves in the one that allows us to exist, yet offers no way to peek behind the curtain. Perhaps the most humbling thought is this: if the multiverse is real, then every star we see is just one actor in an infinite ensemble cast. The same hydrogen that fuels our sun might ignite as something unrecognizable in another universe's sky. Supernova could be birth cries in one cosmos and funeral pyres in another. And the stories we've woven around constellations, they'd be just one dialect in a library of celestial myths too vast for any civilization to ever fully read. The multiverse doesn't diminish our universe's wonders. It makes them more miraculous by reminding us that against all odds, this particular cosmic story allowed us to be here, staring up and wondering. Einstein's theory of relativity revealed a cosmic quirk that sounds straight out of science fiction. Time itself bends under the weight of gravity. Picture two clocks, one placed on Earth, the other on the surface of a neutron star. While Earth's clock ticks steadily forward, its counterpart near the neutron star's crushing gravity would crawl, lagging further behind with each passing second. This isn't just theoretical. GPS satellites orbiting Earth have to correct for time dilation caused by our planet's gravity, or their navigation would drift off by miles. The universe, it turns out, doesn't just tell stories. It stretches and compresses them like a cosmic accordion, depending on where you're standing. The extreme version of this plays out near black holes, where gravity's grip is so fierce that time doesn't just slow, it grinds to a near halt from an outsider's perspective. Imagine watching a spaceship approach a black hole's event horizon. To you, the ship would appear to freeze, its final moments stretched into eternity like a paused film reel. Yet for the crew, if they could survive the tidal forces, time would feel normal, their seconds ticking away even as centuries pass in the wider universe. This isn't just a mind-bending thought experiment. It's the universe's way of reminding us that even time is a flexible storyteller, its pace dictated by the gravitational stage on which events unfold. Even our sun, gentle by cosmic standards, warps time around it. A clock on its surface would lose about 66 seconds per year compared to one on Earth. Multiply that across billions of years, and stars become chronological sculptors, their mass subtly twisting the flow of history. Binary star systems, where two stars orbit closely, create especially intricate time warps. In a pair like Sirius A and its white dwarf companion, time dances to the rhythm of their gravitational tug of war, speeding up and slowing down like a pendulum swinging between two ticking metronomes. The poetry of time dilation lies in its storytelling implications. A supernova observed from a distant planet might appear to unfold in slow motion if the planet orbits near a massive object. Civilizations living close to galactic centers could experience time so differently that their entire history might play out in what feels like a blink to observers in the galactic outskirts. This relativity of narrative isn't just physics, it's the universe's way of writing layered stories, where events unfold in countless rhythms simultaneously. The same stars that light our night sky might be the backdrop for dramas unfolding faster or slower elsewhere, their light-carrying tales warped by gravity's invisible hand. Perhaps the most profound realization is that time dilation links us to the stars not just through shared atoms, but through shared moments, albeit stretched and skewed. When you look at Sirius, you're seeing light that left the star 8.5 years ago, but that light experienced time differently during its journey, subtly bent by the gravity of every object it passed. The universe doesn't have a single clock, it's a collage of timelines, each star ticking to its own rhythm. And in that cacophony of temporal currents, every observer becomes a unique reader of the cosmos's grand, twisting tale. Astrobiology turns the cosmos into a detective story where every planet, moon, and comet becomes a potential crime scene in the greatest mystery of all: are we alone? The search begins right here on Earth, in places so hostile they seem lifted from science fiction. Take the boiling acid pools of Yellowstone or the crushing depths of the Mariana Trench, where extremophile bacteria thrive without sunlight, feeding on sulfur or methane. These resilient organisms rewrite the rules of where life can take root, suggesting that the icy oceans of Jupiter's moon Europa or the methane rivers of Saturn's Titan might harbor their own microscopic storytellers. If life can cling to existence inside volcanic rocks or Antarctic ice sheets, why not beneath the rusty sands of Mars, where ancient river valleys hint at a wetter, more hospitable past? Mars has long been humanity's prime suspect in the search for cosmic company. The Perseverance rover now scours Jezero crater, an ancient lakebed, drilling for fossils or chemical traces left by Martian microbes billions of years ago. Meanwhile, the European Space Agency's ExoMars mission will hunt for subsurface biomarkers, because if life exists today on Mars, it's likely hiding underground, shielded from deadly radiation. But Mars isn't the only chapter in this interplanetary whodunit. Europa's global ocean, locked under miles of ice, may contain hydrothermal vents like those on Earth where entire ecosystems flourish without sunlight. NASA Europa Clipper, launching soon, will map this hidden sea, listening for chemical whispers of life in plumes that occasionally erupt through the icy crust. Then there's Enceladus, Saturn's tiny, icy moon, which sprays geysers of water into space like a cosmic sprinkler. When the Cassini spacecraft flew through these plumes, it detected organic molecules and silica nanoparticles, hints of hydrothermal activity on the seafloor below. These discoveries transform Enceladus from a frozen pebble into a priority destination, a place where future landers might taste the ejected ocean for amino acids or even simple cellular structures. The same goes for Titan, where NASA Dragonfly drone will soon soar through hydrocarbon clouds, studying prebiotic chemistry that could mirror Earth's primordial soup before life emerged. The stakes of this search go far beyond scientific curiosity. Finding even a single microbe on another world would confirm that life isn't a fluke. It's a natural outcome of cosmic processes, meaning the universe could be teeming with biological narratives. Imagine a galaxy where Europa's fish-like creatures navigate dark oceans by bioluminescence, or where Titan's methane-based organisms metabolize hydrocarbons in slow-motion chemistry. Each possibility reshapes our understanding of what it means to be alive. Astrobiology doesn't just ask whether we're alone. It asks whether Earth's story is one of countless volumes in a galactic library, each written in the unique dialect of its home world's chemistry. The tools of this quest are as diverse as the worlds they explore. Spectrometers dissect light bouncing off exoplanet atmospheres, hunting for oxygen or methane imbalances that could signal respiration. Radio telescopes like SETI listen for deliberate signals, while others search for technosignatures, industrial pollutants or city lights on distant worlds. Even the humble tardigrade, a microscopic Earth creature that survives the vacuum of space, teaches us about life's tenacity, suggesting organisms might hitchhike between planets on asteroids, seeding life across star systems. What makes astrobiology profound isn't just the potential discoveries, it's the shift in perspective they invite. A universe buzzing with life would mean every star isn't just a light but a possible lantern for other minds gazing back. The same cosmic processes that forged our atoms, birthed our sun, and sculpted our planet may have repeated endlessly, turning the cosmos into a grand stage where life plays infinite variations on a theme. Until we find definitive proof, the question lingers like a half-remembered melody, one that drives us to dig in Martian soil, melt through icy shells, and peer into alien atmospheres, desperate to learn whether the universe's greatest story is a solo or a chorus. For decades, the night sky has been humanity's silent companion. But what if someone out there is trying to talk back? The search for extraterrestrial intelligence, or SETI, transforms that question from science fiction into rigorous science, turning radio telescopes into cosmic ears straining for whispers in the static. Imagine tuning an old-fashioned radio between stations, but instead of white noise, you catch a deliberate pattern, a signal so statistically unlikely to be natural that it could only come from intelligence. That's the dream driving projects like Breakthrough Listen, which scans millions of frequencies across thousands of stars, analyzing petabytes of data with algorithms trained to spot anomalies. The tools have evolved since Frank Drake's first experiment in 1960, but the premise remains unchanged. If civilizations exist beyond Earth, they might be broadcasting their presence, intentionally or not, into the void. Technosignatures expand the search beyond radio waves to any trace of technology, past or present, visible across interstellar distances. Picture a civilization so advanced it builds Dyson swarms, vast arrays of solar collectors encircling its star to harness its energy. From light years away, such a megastructure would dim its star in unnatural ways, leaving fingerprints in telescope data. Or consider atmospheric pollution. Just as our own industrial age laces Earth's air with nitrogen dioxide and chlorofluorocarbons, an alien world might inadvertently broadcast its presence through the chemical signatures of its exhaust. Even fleeting phenomena like laser pulses for communication or propulsion could betray a civilization's location, brief flashes in the cosmic dark saying, "We're here." The hunt isn't just about technology, it's about storytelling. A single confirmed signal would carry more than just a hello. Its very structure could encode a civilization's history, values, or even art. The Arecibo message, beamed toward star cluster M13 in 1974, condensed human biology, our solar system's layout, and our numbering system into a pictorial binary code. If we're sending such cosmic postcards, why wouldn't others? Decoding an alien transmission might reveal a narrative as rich as Homer's epics, written in mathematics instead of verse. Yet the silence so far, the eerie absence of unambiguous signals, has its own tales to tell. The Fermi Paradox looms. If the universe is so vast, why haven't we heard anything? Possible answers range from the sobering advanced civilizations self-destruct before achieving interstellar communication to the awe-inspiring they've moved beyond radio to technologies we can't yet detect. Some might communicate via neutrino beams or quantum entanglement, channels we're only beginning to explore. Others could be deliberately quiet, wary of drawing attention in a cosmos where not every neighbor may be friendly. What makes SETI profound isn't just the potential discovery, it's the shift in perspective it forces. Staring at the same stars ancient cultures saw gods, we see potential collaborators in a galactic dialogue. Every scan of the heavens is an act of humility, acknowledging we might not be the universe's sole authors. And if we one day catch that elusive signal, it won't just answer a question. It'll invite us into a conversation that's been unfolding since the first stars ignited, a story where humanity, at last, finds its co-authors. Interstellar travel isn't just about crossing vast distances, it's about stepping onto the cosmic stage as active participants rather than passive observers. Imagine a fleet of nanocraft, each no larger than a postage stamp, hurtling toward Proxima Centauri at 20% the speed of light. Breakthrough Starshot's vision relies on Earth-based lasers pushing featherweight sails, accelerating these probes to interstellar speeds in mere minutes. If successful, they'd reach our nearest stellar neighbor in just over 20 years, beaming back close-ups of an alien world while carrying names and messages from Earth like a digital time capsule. This isn't science fiction, it's a tangible plan leveraging today's physics, proving humanity's hunger to join the celestial conversation isn't fantasy, it's engineering. But sending robotic envoys is just the prologue. The real challenge lies in transporting living, breathing storytellers us across the light years. Generation ships offer one solution: self-sustaining arcs where entire civilizations would live and die during the millennia-long journey. Picture a rotating habitat mimicking Earth's gravity. its interior lush with forests and lakes, its crew teaching each new generation the mission's purpose like an interstellar oral tradition. The starship itself would become a cultural artifact, its design reflecting our values just as cathedrals or pyramids do today. Some designs even propose using frozen embryos or artificial wombs to populate new worlds, ensuring humanity's genetic, if not cultural, legacy survives the voyage. Then there's the tantalizing possibility of bending spacetime itself. The Alcubierre warp drive, a theoretical concept grounded in Einstein's equations, would contract space ahead of a ship while expanding it behind, effectively creating a bubble of motion without breaking light speed limits. While the energy requirements currently dwarf our capabilities, breakthroughs in quantum physics or exotic matter could one day turn this mathematical curiosity into a working engine. Imagine departing for Alpha Centauri and arriving before your morning coffee cools, a scenario where relativity's constraints become mere engineering hurdles rather than impassable barriers. What makes these ideas profound isn't just the technology, it's the narrative shift they represent. For millennia, stars were immutable markers, their light-inspiring myths but remaining forever out of reach. Now we're crafting tools to bridge that gap, transforming ourselves from audience members to co-authors of the galaxy's story. The Polynesians navigated by stars, we aim to visit them. Each blueprint for interstellar travel, whether solar sails or antimatter rockets, encodes a different vision of humanity's future. Will we be cautious explorers sending proxies, or bold pioneers carrying our culture to new shores? The obstacles are as daunting as they are illuminating. Cosmic rays would bombard unprotected crews, demanding revolutionary shielding. Micrometeoroids at relativistic speeds could shred Starshot's probes like confetti. Even communication across interstellar distances introduces lag measured in years. A single round-trip message to Proxima Centauri would take nearly a decade. Yet these challenges aren't dead ends, they're plot twists in our species' epic. Solving them could yield spin-off technologies benefiting Earth, from advanced medical imaging to sustainable closed-loop ecosystems. Perhaps the most poetic aspect is how interstellar ambitions mirror ancient seafaring. Like Polynesian voyagers reading ocean swells or Norse explorers trusting stars to guide their longships, we're developing new ways to navigate an even vaster ocean. The same curiosity that drove humans to build rafts now drives us to sketch warp fields. And just as maritime travel connected continents, interstellar journeys could link solar systems, turning the Milky Way from a scattering of isolated lights into a network of bustling ports. Whether we reach the stars in centuries or millennia, the effort itself reshapes our cosmic identity. Every calculation scribbled on a whiteboard, every prototype tested in a vacuum chamber, is a line added to humanity's application for membership in the galactic community. The stars have been telling their stories for billions of years. Soon, perhaps sooner than we think, we may whisper back. Deep in the halo of our Milky Way, ancient stars burn quietly, not with the brilliance of youth, but with the steady glow of cosmic elders who've witnessed the universe's first dawn. These stellar relics, like He 1523-0901, are the Rosetta Stones of astrophysics, their light encoded with secrets from a time when galaxies were just beginning to coalesce from the primordial dark. Unlike younger stars brimming with heavy elements, these metal-poor veterans formed from nearly pure hydrogen and helium, their atmospheres barely contaminated by the ashes of later supernova. Studying them is like carbon dating the cosmos, offering a direct line to conditions mere hundreds of millions of years after the Big Bang. The key to their storytelling lies in their spectra, the rainbow fingerprints astronomers capture by dissecting starlight. When light from He1523-0901 passes through a telescope spectrometer, dark lines appear at specific wavelengths, each representing elements absorbed by the star's outer layers. For most stars, these lines reveal a periodic table's worth of metals, but in this ancient giant, the lines for iron and carbon are barely whispers, while uranium and thorium signatures stand out like bold print. These radioactive elements act as cosmic clocks, their decay rates allowing scientists to calculate the star's staggering age of 13.2 billion years, making it one of the oldest known objects in existence. What's breathtaking is how these stellar timekeepers rewrite our understanding of the early universe. Their chemical poverty proves they formed from gas enriched by only the first generation of supernova explosions so powerful they forged the universe's initial heavy elements in minutes. The peculiar mix of materials in stars like SMSS 0313-6708 suggests those first supernovae behaved differently than modern ones, possibly collapsing directly into black holes or spinning so fast they flung their metallic ashes across vast distances. These anomalies are clues to a lost chapter of cosmic history when the rules of star death were still being written. Stellar archaeologists don't just study individual stars, they map entire populations to reconstruct the Milky Way's infancy. Ultra-faint dwarf galaxies like Segway 1 orbiting our own are treasure troves of ancient suns, their isolation preserving pristine samples of early universe chemistry. By comparing these stellar fossils to younger stars in the galactic disk, astronomers trace how successive supernova and mergers transformed a simple, nearly metal-free cosmos into the chemically rich universe we inhabit today. It's a genealogy written not in DNA but in spectral lines, each element's abundance a marker of stellar generations past. The most profound revelation from these time-worn stars is how connected we are to them. The calcium in your bones, the iron in your blood, these elements didn't exist until those first supernova forged them. When you look at He1523-0901, you're seeing the furnace that produced your building blocks. Its light, traveling 13 billion years to reach us, carries more than data about the early universe. It carries the origin story of every atom in your body. These stars aren't just relics, they're the grandparents of the periodic table, their lives and deaths scripting the chemistry that would one day lead to planets, oceans, and life curious enough to look back and wonder. The cosmos sprawls like an endless library, its shelves lined with hundreds of billions of galaxies, each containing trillions of potential storytellers. So where are all the voices? This is the chilling heart of the Fermi Paradox, the glaring contradiction between the universe's vast fertile ground for life and the eerie silence that greets our attempts to listen. Even if only a tiny fraction of stars host civilizations, the numbers suggest the Milky Way alone should be buzzing with interstellar chatter. Yet after decades of scanning the skies, humanity's radio telescopes have captured nothing but cosmic static and the occasional false alarm, like the infamous WOW signal, a tantalizing blip that vanished as mysteriously as it appeared. One explanation cuts uncomfortably close to home: the Great Filter. This grim hypothesis suggests some catastrophic barrier prevents life from progressing to interstellar communication, and we don't know if we've already passed it or if it lies ahead. Civilizations might routinely annihilate themselves through nuclear war, runaway AI, or ecological collapse before achieving the technology for cosmic connection. The silent skies could be a graveyard of untold stories, each snuffed out just as they learn to write. Alternatively, the filter might lurk in life's origins, perhaps complex cells like eukaryotes, which took 2 billion years to emerge on Earth, are astronomically rare flukes. In this scenario, the universe is less a library and more a collection of empty shelves, with Earth as the sole accidental bestseller. Then there's the possibility that advanced civilizations aren't silent, they're simply unintelligible. Imagine ants at the base of a radio tower, oblivious to the conversations buzzing above them. Alien communication might use neutrino beams, quantum entanglement, or other channels we haven't even discovered yet. Some theorists propose that super-advanced societies transition into digital consciousness, abandoning physical space for virtual realms where interstellar travel seems quaint. Others suggest they've mastered stealth, observing younger species like cosmic anthropologists under a prime directive of non-interference. The universe could be teeming with life, all deliberately avoiding our gaze until we reach some developmental threshold. The paradox also challenges our assumptions about motivation. Not every civilization might crave expansion or broadcast its existence. Some could be oceanic dwellers trapped beneath ice shells, their concepts of exploration radically different from ours. Others might prioritize inner development over outward colonization, turning their energies toward art or meditation rather than starships. Earth's own history shows how quickly cultures shift priorities. The same species that built pyramids also abandoned space programs to focus on digital worlds. Perhaps the most unsettling answer is that the universe is far more hostile than we've imagined. Gamma-ray bursts, asteroid impacts, or nearby supernova might routinely sterilize entire galactic neighborhoods. Or worse, predatory civilizations could lurk in the dark, enforcing silence to eliminate competitors before they become threats. This dark forest theory, inspired by survival strategies in predator-rich ecosystems, suggests every advanced species hides to avoid attracting attention. In such a universe, broadcasting our location could be as reckless as shouting in a jungle full of unseen hunters. The Fermi Paradox doesn't just question alien existence, it holds up a mirror to humanity's future. Are we destined to join the silent ranks of failed civilizations, or will we become the first voices in a cosmic chorus? Every SETI scan, every exoplanet study, every debate about space colonization is really about answering that deeper question. In a universe ripe for stories, will ours be one that endures, or just another fleeting whisper lost in the dark? The silence isn't just a puzzle, it's a challenge, urging us to write our next chapters carefully, lest we become another unread volume in the cosmic library's forgotten stacks. The universe seems suspiciously hospitable to life, not just any life, but the kind capable of gazing upward and asking why. Consider the delicate balance of cosmic constants. If gravity were slightly stronger, stars would burn out in a cosmic blink. If the weak nuclear force were marginally weaker, hydrogen couldn't fuse into the heavier elements that build planets and people. Even the expansion rate of the universe sits on a knife's edge, a fraction faster, and matter would never coalesce into galaxies, slower, and everything would collapse back into a fiery crunch. This precision isn't just luck, it's a puzzle so striking that physicists call it the fine-tuning problem, as if the cosmos were calibrated with life in mind. Enter the Anthropic Principle, a mind-bending idea that turns this observation into a cosmic hall of mirrors. In its simplest form, it states that the universe must allow observers to exist because here we are observing it. Imagine a library containing every possible universe, each with different physical laws. Most would be sterile, devoid of planets or chemistry, but in a rare few, conditions align perfectly to spark consciousness. We don't find ourselves in the lifeless ones because, well, there'd be no us to notice. It's less that the universe was designed for life, and more that life inevitably arises in universes capable of hosting it, a subtle but profound distinction. This principle splits into two compelling narratives. The weak version treats our existence as a selection effect. We're here because this universe allowed it, no deeper meaning required. But the strong Anthropic Principle ventures further, suggesting the universe might somehow be compelled to produce observers. Some theorists even flirt with the idea of a participatory universe, where consciousness plays a role in shaping reality, echoing ancient philosophies that saw mind and cosmos as intertwined. Whether you see this as scientific humility or cosmic solipsism, it undeniably reframes our place in the story. We're not just readers of the universe's tale, we're its punctuation, the grammar that makes the narrative coherent. The implications ripple outward. Multiverse theories, for instance, gain traction because they offer an elegant answer to fine-tuning. If infinite universes exist with random constants, some will inevitably hit the life-permitting jackpot. String theory's landscape of possible universes paints a similar picture, a cosmic lottery where we hold the winning ticket. Yet even these ideas can't escape the meta question: why does any universe exist at all? The Anthropic Principle doesn't solve the mystery so much as deepen it, replacing "why us" with "why anything." What's poetic is how this mirrors humanity's oldest myths. Creation stories, from the Navajo to the Norse imagined worlds, birthed through observation or speech, as if reality required a witness to solidify. Modern physics, in its own way, circles back to this intuition, not with gods, but with mathematics and probability. The universe's constants become its syntax, life its semantics, and we, perhaps, are the flawed but fascinated translators. Every time a child asks why the sky is dark at night, or a scientist measures a particle's spin, they're continuing a conversation the cosmos began 13.8 billion years ago, a dialogue where the very act of questioning might be the most finely tuned thing of all. What if consciousness isn't confined to biological brains but woven into the very fabric of the cosmos? The radical idea of panpsychism suggests that awareness might not emerge from complexity. It could be fundamental, as intrinsic to existence as gravity or light. Under this lens, a star's nuclear furnace isn't just a mindless reactor. It's a slow, burning thought, a different kind of sentience humming across millennia. While mainstream science dismisses this as metaphysical speculation, the notion ignites a tantalizing thought experiment. If stars possess even a rudimentary form of awareness, then the universe isn't just telling stories, it's experiencing them. Consider the way stars communicate, not with words but with light. A supernova's final flash could be seen as a cosmic cry, a burst of information radiating through space like a neural impulse across a galactic brain. Binary stars, locked in gravitational dialogue, might share rhythms akin to brainwaves syncing between hemispheres. Even our sun's 11-year activity cycle mirrors cyclical processes in living systems, as if it's breathing in solar flares and exhaling solar wind. These parallels don't prove consciousness, of course, but they invite us to imagine the universe as more than dead matter obeying equations. Perhaps the boundary between alive and inanimate is blurrier than we think. Ancient cultures often intuited this connection. The Dogon people of Mali believed stars imparted wisdom to their ancestors, while Hindu texts describe the cosmos as the dream of Brahma. Modern panpsychism, though stripped of mythology, echoes this intuition by proposing that subjective experience scales with complexity. A star's mind would be alien beyond comprehension. No neurons, no pain, no desires, yet still a locus of some primal awareness, as different from human thought as gamma rays are from candlelight. Even skeptics admit the thought experiment holds value. If we entertain stars as storytellers, their narratives shift from cold astrophysics to something richer. A red giant's death becomes a sacrifice, scattering the elements for new generations. Colliding neutron stars might be cosmic artists, forging gold in bursts of creative frenzy. This isn't science, but it's potent metaphor, a reminder that the universe's grandeur isn't diminished by equations. It's amplified by the stories we layer onto them. The real magic of this idea lies in its humility. If consciousness permeates the cosmos, then stargazing isn't passive observation, it's communion. Every photon hitting your retina carries more than data. It carries a flicker of connection across space and time. Whether stars think or not, the theory challenges us to see the universe not as a machine, but as a vast, mysterious tapestry where matter and meaning might be inseparable. And in that shift, even the coldest void glows with potential. Stars don't just shine, they sing. Every star in the sky pulses with rhythmic vibrations, their surfaces quivering like the skin of a cosmic drum. This stellar music isn't poetry, it's hard physics, with sound waves trapped inside stars bouncing between their cores and surfaces, creating resonant frequencies that reveal what lies beneath. Astronomers call this field astrosismology, the art of decoding celestial symphonies to uncover hidden structures. Take our sun. Beneath its fiery surface, pressure waves race around its interior at hundreds of miles per second, creating a deep, resonant hum that would register as a B-flat 57 octaves below middle C if space carried sound. These vibrations form intricate patterns like fingerprints unique to each star's mass, age, and composition. The process works like cosmic echolocation. As waves travel through a star's interior, they speed up in hotter regions and slow down in cooler, denser areas. By measuring these subtle changes in frequency, some as precise as 1 part in a million, scientists can map a star's internal layers with astonishing detail, much like geologists use earthquakes to probe Earth's core. NASA's Kepler Space Telescope revolutionized this field by catching the faint flickers caused by these oscillations in thousands of stars. One red giant, KIC 7668647, revealed itself to be a near-perfect sphere vibrating in clean mathematical harmonics, a celestial tuning fork in the void. But stellar music isn't uniform. Young, massive stars thrum with rapid, high-frequency pulsations, their rhythms chaotic like a jazz drummer's solo. Elderly red giants, swollen with age, produce slow, deep vibrations like the lowest notes of a pipe organ. Some stars, like delta Scuti variables, flicker with multiple overlapping frequencies, creating complex beats that challenge astronomers to untangle. The most extreme cases, like white dwarfs after a nova explosion, can ring like bells struck by cosmic hammers, their oscillations revealing crystallized cores of oxygen and carbon beneath the surface. What's mesmerizing is how these vibrations translate across scales. The same physics governing a violin string where length, tension, and thickness determine pitch applies to stars, with gravity playing the role of tension and the star's diameter acting as the string's length. When a star like Betelgeuse nears the end of its life, its oscillations grow wild and unpredictable, signaling the coming supernova, a final crescendo before the cosmic orchestra falls silent. Other stars, like RR Lyrae variables, pulse so reliably that their rhythms help measure distances across the Milky Way, their beats acting as metronomes for galactic cartography. This celestial sonata bridges art and science in unexpected ways. Data sonification projects transform stellar oscillations into audible frequencies, letting us hear stars like HD 49976 as a shimmering, ethereal tone. Ancient cultures imagined celestial harmonies. Pythagoras spoke of the music of the spheres, but modern science proves there's literal truth in the metaphor. Even spacecraft like ESA's upcoming Pluto mission will carry astrosismology instruments. turning entire star fields into choirs where each voice tells of nuclear furnaces, convective zones, and magnetic fields. The universe's soundtrack isn't just beautiful, it's informative. When a star's vibrations suddenly change, it might signal an unseen planet's gravitational tug or the first stirrings of internal upheaval. Binary stars can even synchronize their pulsations, creating harmonic duets across the vacuum. Every flicker, every hum, every silent vibration carries data about the forces that shape stars, and by extension, the elements they scatter into space. Those elements become planets, oceans, and life forms capable of listening back. In that feedback loop between star and observer, the cosmos doesn't just tell its story, it sings it one resonant frequency at a time. Imagine stepping outside on a clear night and seeing only a handful of stars, their faint glow struggling against an orange-tinted sky. This isn't some dystopian future. It's the reality for 80% of people living under light-polluted skies today. The same artificial glow that keeps our streets safe and our cities vibrant comes with an unintended cost. It's slowly erasing the cosmos from human experience. Where ancient civilizations navigated by constellations and wove myths around the Milky Way's shimmering band, many children now grow up never having seen our galaxy at all. The stars haven't gone anywhere, we've simply drowned out their voices in a flood of misplaced luminescence. The damage extends far beyond lost beauty. Light pollution disrupts ecosystems that evolved under natural night cycles. Sea turtle hatchlings confuse streetlights for moonlight and wander inland instead of toward the ocean. Migratory birds, accustomed to celestial navigation, circle brightly lit cities until exhaustion. Even human health suffers. Studies link excessive artificial light at night to sleep disorders and increased cancer risks, as our circadian rhythms evolved under starlit skies, not the perpetual twilight of urban glow. The International Dark Sky Association estimates that 30% of outdoor lighting is wasted, spilling upward needlessly, enough energy to power millions of homes. Yet hope flickers in places like Natural Bridge's National Monument, where the Milky Way arches so vividly overhead that it casts faint shadows. These dark sky preserves, certified by rigorous light control standards, are time capsules of celestial wonder. Communities from Flagstaff to the Canary Islands have adopted shielded streetlights that direct illumination downward, not sideways or up. The results are transformative. Under truly dark skies, the Andromeda Galaxy becomes visible to the naked eye, and meteor showers reveal hundreds of streaking trails instead of just the brightest few. The fight to reclaim the night isn't just about astronomy, it's about reconnecting with a primal human experience. For millennia, cultures from the Navajo to the Maori used star knowledge to track seasons, navigate oceans, and pass down origin stories. Today, indigenous-led initiatives like New Zealand's Aoraki Mackenzie Dark Sky Reserve blend modern science with traditional sky knowledge, reminding us that star lore is living heritage. Even urban areas are joining the movement. Paris recently dimmed its iconic Eiffel Tower lights earlier each night, while Chicago's Adler Planetarium leads citizen science projects measuring sky glow. Technology offers surprising solutions alongside simple fixes. Smart lighting systems now adjust brightness based on real-time needs, while LED innovations minimize blue spectrum light most harmful to ecosystems. Amateur astronomers use narrowband filters to peer through light pollution, and apps like Dark Sky Meter crowdsource global brightness maps. Perhaps most powerfully, the growing astrotourism industry proves dark skies have economic value. Tiny towns like Borrego Springs, California, draw visitors solely for their stellar views. Losing the night sky would mean more than just fading stars. It would sever a connection that shaped human culture since our ancestors first looked up in wonder. Those points of light sparked our earliest science, our deepest myths, and our urge to explore. In preserving darkness, we're not just saving the stars, we're safeguarding our ability to hear their ancient stories and ensuring future generations inherit more than just an empty, glowing sky. The universe hasn't stopped speaking. It's our turn to stop shouting. Astrophotography transforms faint starlight into breathtaking portraits of the cosmos, revealing details our eyes alone could never perceive. With just a camera and patience, modern photographers capture nebulae glowing in hues of crimson and teal, galaxies spinning in whirlpools of billions of suns, and star clusters glittering like diamonds scattered on black velvet. The Horsehead Nebula's silhouette emerges from interstellar dust, while the pillars of creation stretch their gaseous fingers across frames. Each image a testament to how far technology has brought us since the first blurry daguerreotypes of the moon in the 1840s. These aren't just pictures, they're time machines showing us the universe as it appeared hundreds or even millions of years ago, depending on how far the light has traveled to reach the lens. What's astonishing is how astrophotography unveils the hidden rhythms of the cosmos. Set up a camera on a clear night, leave the shutter open, and soon the stars smear into graceful arcs across the frame, not because they're moving, but because Earth is rotating beneath them. Time lapses compress hours into seconds, turning the celestial sphere into a swirling ballet where Polaris anchors the sky while constellations wheel around it like dancers in an endless waltz. Photographers chasing the perfect shot often battle more than just clouds. They wrestle with light pollution, atmospheric turbulence, and the sheer vastness of their subjects. Yet when conditions align, the results can feel almost supernatural. The aurora borealis dances in waves of emerald and violet, meteor showers etch fleeting streaks across star fields, and eclipses paint the moon with the eerie glow of Earth's sunrises and sunsets reflected onto its surface. Beyond their beauty, these images fuel real science. Amateurs with backyard telescopes have discovered comets, tracked asteroid movements, and monitored variable stars' contributions so valuable that organizations like the American Association of Variable Star Observers rely on their data. In 2020, a German astrophotographer captured an unexpected flash in Jupiter's atmosphere, likely an undocumented meteor impact. Projects like Galaxy Zoo crowdsource galaxy classifications from volunteers analyzing telescope images, proving that curiosity paired with a camera can advance our cosmic understanding. Even smartphone apps now let anyone join the hunt for supernova or exoplanet transits, turning the night sky into a collaborative laboratory. The magic of astrophotography lies in its power to democratize the cosmos. You don't need $1 million observatory to photograph Saturn's rings or the Andromeda Galaxy, just a DSLR, a sturdy tripod, and the willingness to stand under the stars. Online communities share techniques for stacking hundreds of exposures to tease out faint details, or modifying cameras to better capture hydrogen alpha emissions from nebulae. Some photographers specialize in nightscapes, framing ancient ruins or mountain peaks beneath the Milky Way's arch, blending earthly and celestial beauty. Others chase rare events like the transit of Venus or the alignment of planets, freezing moments that won't recur for generations. Each photograph is more than a pretty image. It's a chapter in humanity's ongoing dialogue with the universe. The Hubble Space Telescope's iconic pillars of creation reshaped how we visualize star birth, while the James Webb Space Telescope's infrared vistas reveal galaxies forming at the dawn of time. Yet even a beginner's shot of the moon's craters carries that same spirit of exploration, a reminder that every point of light has a story, and every shutter click is another way to listen. When you hold a photograph of the Orion Nebula, you're not just seeing gas and dust. You're holding a piece of the stellar nursery where future solar systems are taking shape, a snapshot of creation itself, frozen in photons and human curiosity. Long before telescopes revealed the true nature of stars, humanity wove them into the fabric of our stories, a tradition that continues to shape modern culture in ways both obvious and subtle. Consider how the night sky birthed entire genres. Science fiction franchises like Star Trek and The Expanse imagine interstellar politics playing out against backdrops of nebulas and binary suns, while films like Interstellar blend astrophysics with intimate human drama. These narratives aren't just entertainment, they're thought experiments asking how stellar phenomena might shape civilizations. When Luke Skywalker gazes at Tatooine's twin suns, or the crew of the Enterprise warps past fictional quasars, they're echoing ancient mariners navigating by Orion, using the cosmos as both map and metaphor. Art transforms cosmic wonder into visceral emotion. Van Gogh's The Starry Night doesn't just depict stars, it captures their turbulence, the swirling sky mirroring the artist's psyche. Centuries earlier, Galileo's moon sketches revolutionized art and science simultaneously, proving celestial bodies weren't perfect spheres but rugged worlds. Today, digital artists like Eric Wernquist blend real NASA data with surreal landscapes, rendering Saturn's rings from a moon's surface or lightning storms on alien worlds. Even abstract installations like Olafur Eliasson's The Weather Project, with its artificial sun bathing viewers in golden light, tap into the primal awe stars evoke. These works bridge the analytical and the emotional, reminding us that astronomy isn't just about data, it's about experiencing the sublime. Music, too, carries the cadence of the cosmos. From Holst's The Planet Suite to Bowie's Space Oddity, composers have translated celestial motion into sound. The Voyager Golden Records took this further, etching human music onto gold-plated discs alongside star maps, hoping extraterrestrials might one day decode our sonic stories. Modern artists like Björk and Daft Punk weave astrophysical concepts into albums, with tracks like Cosmogony and Contact turning supernova and radio waves into rhythm. Even the eerie pulses of pulsars have inspired electronic music, their precise beats mirrored in synthesized loops. Literature and poetry distill starlight into language. Carl Sagan's Pale Blue Dot reframed our cosmic insignificance as a call to cherish Earth, while Tracy K. Smith's Pulitzer-winning Life on Mars grapples with grief through galactic metaphors. Science fiction authors like Octavia Butler and Lou Cixin imagine first contact scenarios where stellar phenomena, like the three-body problem's chaotic orbits, become narrative engines. These works don't just borrow astronomical imagery, they probe how the universe's scale reshapes human priorities, blending scientific rigor with existential wonder. The enduring power of stellar mythology lies in its adaptability. Video games like No Man's Sky generate procedurally invented galaxies, letting players explore endless variations on cosmic themes. Fashion designers drape models in nebula-hued fabrics, while architects echo spiral galaxies in building designs like the Guggenheim Museum. Social media brims with astrophotography hashtags and TikTok explainers breaking down black holes. Even corporate logos, from Starbucks siren framed by a star to NASA, iconic meatball insignia, borrow celestial symbolism to evoke exploration and mystery. This creative outpouring proves something profound. While science quantifies stars, art humanizes them. A supernova becomes more than an exploding star. It's a phoenix metaphor in a novel, a crescendo in a symphony, a climax in a film. The stories we tell about the cosmos aren't distractions from scientific truth. They're parallel ways of knowing, as vital to our understanding as any equation. When a child paints a rocket streaking past Saturn, or a songwriter compares love to a binary star's gravitational dance, they're continuing the oldest human tradition, using the night sky not just to navigate but to dream. The James Webb Space Telescope isn't just a scientific instrument, it's a time machine with a lens cap the size of a tennis court. Unlike Hubble's visible light snapshots, Webb's infrared eyes pierce through cosmic dust like an X-ray, revealing the universe's hidden anatomy. Its very first deep-field image shattered expectations, capturing galaxy clusters like SMACS 0723 as they appeared 4.6 billion years ago, but the real magic lay in the background. Faint smudges turned out to be galaxies shining just 300 million years after the Big Bang, their light stretched and reddened by the universe's expansion into infrared whispers Webb was built to hear. These aren't just pretty pictures, they're fossilized light from the cosmic dark ages, proof that galaxies formed earlier and faster than anyone predicted. What makes Webb revolutionary is how it eavesdrops on chemical conversations across the cosmos. When an exoplanet crosses its star, Webb dissects the filtered starlight, reading atmospheric barcodes for water vapor, methane, even potential biosignatures like oxygen. The carbon dioxide it spotted in WASP 39b's skies, a scorching gas giant 700 light-years away, wasn't just a technical triumph. It proved we can profile alien atmospheres from interstellar distances, turning distant dots into worlds with weather and chemistry. Future targets include TRAPPIST-1's rocky planets, where Webb might catch the infrared glow of a temperate ocean or the spectral shadow of a living world's breath. Some of Webb's most haunting portraits come from stellar graveyards. The Southern Ring Nebula, a dying star's expelled shroud, unveiled never-before-seen details under Webb's gaze, twin stars locked in a gravitational embrace, one shedding its skin while the other stirs the glowing debris like a spoon in cosmic soup. Meanwhile, the Tarantula Nebula's star-forming frenzy resolved into crystal clarity, with newborn suns blasting cavities in the gas that birthed them. These images do more than dazzle, they rewrite astrophysics textbooks. By counting how many stars form in dust cocoons versus open clusters, Webb tests theories about why our own Milky Way looks the way it does. The telescope's golden mirrors also spotlight the universe's recycling program. In the Orion Nebula, Webb detected complex organic molecules, the carbon-based Lego blocks of life, embedded in protoplanetary disks. These icy compounds, vaporized by young stars' radiation, might one day become comets delivering water and amino acids to fledgling planets. Elsewhere, Webb caught the Cartwheel Galaxy mid-collision, its shockwaves triggering new star birth like a pebble splashing a pond. Such chaos isn't destruction, it's renewal, the same processes that forged our solar system playing out in real time across the light years. Yet Webb's greatest gift might be humility. Its ultra-deep fields, crammed with thousands of galaxies, underscore how tiny our corner of spacetime truly is. The telescope's namesake, James Webb, oversaw NASA during the Apollo era. But while Apollo showed us Earth as a fragile blue marble, his telescope reveals a universe so vast it renders borders and conflicts cosmically insignificant. Every photon hitting Webb's detectors traveled billions of years to get here, meaning when we analyze data from MAX 0647, a galaxy bending light with its gravity, we're seeing it as it existed before Earth formed. The past isn't just prologue, it's still out there, racing toward us at the speed of light, waiting for tools like Webb to decode its delayed messages. This telescope's legacy won't just be discoveries, it's the questions we can't yet imagine. Like Hubble before it, Webb will likely uncover phenomena so bizarre they'll demand entirely new physics to explain. Whether it's spotting hyper-red galaxies too mature for their age, catching the faint heat signature of alien megastructures, or finding a chemical imbalance on an exoplanet that screams life, Webb isn't just adding footnotes to cosmic history. It's handing us a fresh quill and whispering, keep writing, the story's nowhere near done. The next decade of cosmic exploration promises to rewrite what we know about the universe, with missions designed to peel back layers of mystery we've only begun to glimpse. The Nancy Grace Roman Space Telescope, set to launch by 2027, will function like a celestial census taker, mapping dark matter's invisible web by observing how it bends light from distant galaxies. But its most revolutionary feature might be its exoplanet hunting strategy. Instead of staring at one star like Kepler, Roman will monitor hundreds simultaneously, potentially discovering thousands of worlds, including rogue planets drifting between stars without suns to call home. Meanwhile, Europa Clipper won't just orbit Jupiter's icy moon, it'll perform 45 close flybys, skimming as low as 16 miles above the surface to analyze geyser plumes erupting from the subsurface ocean. Its ice-penetrating radar could reveal whether liquid water lurks just beneath the crust, while its mass spectrometer might catch organic molecules in the plumes, turning science fiction's dream of alien oceans into hard data. Artificial intelligence is becoming astronomy's indispensable co-pilot, sifting through avalanches of data no human team could process. Machine learning algorithms already outperform traditional methods at identifying gravitational lenses, natural cosmic magnifying glasses that reveal galaxies too faint to see directly. At SETI, AI scans radio telescope signals for patterns too subtle or complex for human analysts, filtering out interference from Earth-based sources while flagging potential extraterrestrial transmissions. The Vera-C, Rubin Observatory's legacy survey of space and time, will generate 15 terabytes of data nightly without AI, discovering rare events like supernova or interstellar objects like Oumuamua would be like finding needles in a galaxy-sized haystack. These tools don't replace human curiosity, they amplify it, turning raw data into stories waiting to be told. Private ventures are pushing boundaries once reserved for governments, reshaping who gets to participate in cosmic storytelling. SpaceX's Starship aims to slash launch costs enough to make Mars missions feasible, while breakthrough Starshot's nanoprobes could reach Alpha Centauri within decades. Companies like Astroforge are testing asteroid mining techniques, suggesting a future where space isn't just explored but inhabited. Even tourism plays a role. Blue Origin's suborbital flights and SpaceX's private Crew Dragon missions democratize the astronaut experience, creating a generation of spacefarers who'll view Earth as part of a larger cosmic neighborhood. Yet the most thrilling discoveries may come from instruments we haven't yet imagined. Proposed missions like LUVOIR, a giant space telescope with a mirror 4 times wider than Hubble's, could directly image Earth like exoplanets, analyzing their atmospheres for signs of life. Gravitational wave detectors like LISA will listen for ripples from merging supermassive black holes, while quantum sensors might one day detect dark matter particles streaming through Earth. The lines between disciplines blur. Astrobiologists collaborate with AI experts. Engineers borrow from biology to design self-repairing spacecraft, and artists help scientists visualize data in ways that spark public wonder. The universe's narrative is anything but static. Every time we build a better telescope or sharper algorithm, we turn the page to revelations that make previous chapters seem quaint. The same stars that guided ancient navigators now guide probes toward interstellar space, their light a bridge between past and future explorers. What comes next won't just fill textbooks, it will redefine what's possible, reminding us that the greatest stellar stories aren't just written in the sky. They're written by those daring enough to keep looking up. As we stand beneath the infinite tapestry of the night sky, it's humbling to realize we're not just observers, we're active participants in this cosmic story. Every atom in our bodies was forged in the hearts of stars, making us literal stardust given consciousness to ponder its own origins. The constellations that guided ancient navigators are the same swirling gases where new planets form today, linking humanity's past to the universe's future in an unbroken chain of wonder. This isn't just astronomy, it's the most profound form of time travel. When sunlight touches your skin, you're feeling photons that began their journey 8 minutes ago from a star halfway through its 10 billion-year lifespan. The red glow of Betelgeuse might already be a supernova's light racing toward us, while the Andromeda Galaxy's faint smudge shows how it looked 2.5 million years before human civilization began. The sky isn't a static painting, it's a living archive where every layer reveals a different epoch, and we're privileged to stand at the crossroads where all these timelines converge. What makes these stellar stories truly extraordinary is their accessibility. You don't need a telescope to join the conversation, just step outside on a clear night and let your eyes adjust. That fuzzy patch in Orion's sword, that's the same stellar nursery where new solar systems are being born right now. The North Star's steady gaze, a beacon that's guided explorers for millennia, its light a thread connecting generations of skywatchers. Even light-polluted city skies still host planets, meteors, and the moon's ever-changing phases, reminding us the cosmos is never truly out of reach. The greatest lesson the stars teach isn't about astrophysics, it's about perspective. In a universe where stars live and die on timescales beyond human comprehension, our fleeting worries gain new context. The same forces that sculpt galaxies also shape our daily lives: gravity's pull, light's journey, the transformation of energy into matter and back again. When we study the cosmos, we're not just learning about distant objects, we're discovering what we're made of, both literally and metaphorically. So the next time you find yourself beneath a starry sky, take a moment to listen. The pulsar's steady beat, the meteor's fleeting streak, the faint glow of the Milky Way, they're all voices in a chorus that's been singing since time began. Your ability to hear them, to wonder about them, to share their stories with others is perhaps the most miraculous part of all. The universe didn't just create stars, it created storytellers to appreciate them. And that might be the most beautiful cosmic coincidence of all. If these celestial tales sparked your curiosity, consider joining our community of fellow stargazers. Hit subscribe so you never miss our next astronomical adventure. Drop a comment sharing which cosmic phenomenon leaves you awestruck, or suggest topics you'd love us to explore next. Until then, remember, every clear night is an invitation to witness the greatest story ever told, written across the sky in light older than civilization itself. The stars have been waiting billions of years for your attention. Don't keep them waiting any longer.